Okay, so let's start. Uh, Today will be a kind of light class. I won't be teaching much difficult concepts, just one new concept which we'll be looking into, that is statistical testing, which is very important. As you will also see in scientific papers, we not only report our results, like the what accuracies we have obtained, but also we do a statistical analysis to say whether they are really significant or not. So I'll tell you the meanings of these terms in a while. But let's quickly revise what we had studied before. So we saw different techniques for primarily two problems. So this was the paper which we were going through: detection and classification of acoustic scenes and events. So you are classifying different acoustic scenes. That is one problem. Another problem is detecting individual events which are happening in the scene. For example, clapping or sneezing or speaking or music playing in the background. We saw bag of frames approach, where you are not concerned with the temporal ordering, but with what? Co-occurrence of things together. Then we considered the polyphonic case, when many signals are additively overlapping. They're not blocking each other or covering each other, but they are superposed and they can be separated linearly, let us say. So this is polyphonic analysis. So the best approach which we have studied so far of polyphonic analysis is PLCA or NMF, because they can do linear separation. So the baseline approach which this paper had considered for both these problems, it was that you have an audio recording, which is your, let's say, training or test file. So you first of all decompose it using your dictionaries, NMF dictionaries, to create a activation vector, which is your representation or feature vector for that file or for that frame. And then you use these feature vectors for further processing, which is classification or detection, right? Is this clear? Like, these are just the things which we have already discussed. And then we saw, the baseline method basically was this. And then we saw different kinds of evaluation metrics. You can evaluate frame-wise, that at each time frame you see if you are identifying all the events correctly or not. Another approach was event-wise, like in the entire audio, let's say there's only a single event happening, then you see whether what you are detecting, are you able to detect that event or not. So the criterion used is, okay, you are only looking at the onset time. The onset time, what you have detected and what the ground truth is, if they are within 100 milliseconds, then you say, yes, this is correctly detected. And you're not concerned about the offset time. The third metric is also concerned about the offset time, which means you're not only looking at the start of the event, but also at the end of the event, the estimation. Okay, so based on these, you defined various metrics, and then we saw some of the challenges, practical challenges in data collection, data preparation, and then running the tests, basically running the submissions from different research groups. And then finally, we came to this results section. The overall results for classification, scene classification task is given here. So you can see on the x-axis, we have different algorithms which were submitted. Maybe I'll make it a little bit bigger. X-axis has all the different algorithms which were submitted by different research groups. On the y-axis, we have the accuracy obtained by these algorithms. Let us say my test set has 100 files. How do I measure the accuracy? Okay, I have some metric, I have some method to compute accuracy. I will compute it for each and every file. Let's say for this file, is it able to detect all the events correctly or not based on that? And in this way, I compute the accuracy for all the files, but that will give me a single value of accuracy. But I want a statistic I want multiple values of tests across which I can compare. Okay. So how we do it here is, let's say in this case they're doing 5-fold cross-validation, which means because training is not done by them, training is done by the researchers individually, so they cannot do training again. So they have got trained models. Now they are running, let's say 20 samples at a time. So to make it five-fold cross-validation, means you have 100 samples. You take randomly any 20 samples, make 5 sets of 20 samples each. Randomly make 5 sets. And then evaluate each algorithm on the first set, compute the accuracy. Then on second set, compute the accuracy. In this way, for each algorithm, you will have 5 sets of accuracies, right? And then you can compare them across each other, that whether they are statistically significant or not. It is possible that okay, I think I should give a concrete example for this. Okay. So let us say we have got 2 distributions. These are the accuracy values, let's say. One distribution is, I'm drawing it in 2 dimensions, but the x dimension is just not valid. Let us say this is first algorithm. And this is the second algorithm. The accuracies. This is for the first algorithm, this is for the second algorithm. What do you say? Which one is better? Which one is better? Means you cannot say, right? Both are almost similar. But let us say, because these tests are done on, let's say, many, like thousands of test files. This is what you obtain. But in practically doing, you will be doing only with 5 sets, right? Let's say these are 1,000 sets. So you find out that, okay, they are really same. But you won't be doing it for 1,000 sets practically, right? You will be doing only for 5 sets or 5 to 10 sets at most. So it's possible that when you are sampling from this algorithm, you sampled this set, you sampled this set, you sampled this set, you sampled maybe this set, you sampled this set, right? And corresponding values for these sets is one is here, one is here, one is here, one is here, let's say one is here. Now what is the mean? For this one, the mean will be somewhere here, right? For this one, the mean will be somewhere here. So when you did your testing, you find out that for my blue algorithm, my mean accuracy is this much. But for my green algorithm, the mean accuracy is this much. So what you can say clearly, looking at just these 5 sets of accuracies, what will you say? The blue one is better, right? The blue algorithm is better than the green algorithm. But if you take more and more sets and you do really huge test, then you will come to know, no, these are actually both same. So is there a way to take care of this problem? Is there a way to quantify, if I am saying blue one is better, how much confident I am? Or how much statistically significant is this assumption or this hypothesis that blue one is better than green one? Yeah. What are the factors which will decide that? What are the factors which will tell you about the confidence? Confidence in your hypothesis. Hypothesis means my hypothesis is that, okay, let us say blue one is better than green one. What are the factors? One is sample size. You're not able to see the underlying distribution. You're only seeing these 5 red marks on the blue, 5 red marks on the green. That's it. One is sample size, because if you make your sample size instead of 5, make it 500, then you are more sure, you're more confident that yes, this is indeed better or not. Pardon? Once again? Huh. Are they the?
So you said something like those crosses in the green ones, they correspond to those crosses in the blue ones.
Yeah.
So what do you mean by that?
Okay, what do I mean by that? Good question. So let us say I chose my first test set of 20 samples. Oh, means if you remember, 100 samples were there in all. I made 5 sets of 20 samples each. I took the first set, I ran my algorithm, the blue algorithm. I got a value of accuracy. Let us say that value of accuracy is this one, right? On the same set, I ran my green algorithm. And for the green algorithm, the accuracy was, let's say, this one, right? Similarly, I do it for the second set, third set, this way 5 sets.
Those 5 sets were choosing randomly?
Yeah, they were chosen randomly. Randomly means I have, let's say in this case, I'm doing experiment on scene classification. Let's say I want to classify whether it is classroom or roadside, right? So what will I do? I will record some samples out of infinite possibilities in which I can record the samples. I will choose, okay, let me record one sample at 5 p.m. on Wednesday evening, one sample on 6 p.m. on Tuesday morning, something like that. So Tuesday evening, something like that, right?
What I was like out of this 100, you created 5 sets by 28.
Yes.
So what am I like, are you picking those 20 randomly?
Randomly, yes. Yeah, randomly. So whenever we are doing testing, it is good to introduce as much randomization as possible so that we are more and more unbiased. Okay. So what decides how will you be confident that your hypothesis is correct? If your sample size increases, your confidence will go up. What else? What else? Huh? Sample values, yes. Sample variance. Sample variance means the intra-class variance. The intra-class variance of samples. Yeah, maybe, yes. Then what else? One very obvious thing. The distance between the means, the difference. If the difference is large, you can be more confident that yes, this must be true. Right? If I take 5 samples, the difference between the two values, the two means, is very small, then my hypothesis that green one is, the blue one is better than the green one, I'll be less confident, right? Because the difference is so small. But if the difference is very large, I'll be more confident. Yes, it must be true because given these 5 random sets, it is very unlikely that the difference should be small. Means if the difference is large, then I will be more confident that yes, this must be better.
So will that come in sample size?
No.
Then what does sample size?
Sample size means in this case, sample size is 5. I have only 5 sets.
Increasing
Or
sample size,
in other words, okay, I have 5 sets of 20 samples each.
But how does that increase your confidence in any hypothesis?
What? Okay, if you take more samples, let's say I take 500 samples, and still I get difference, right? Then I will be more confident that yes, even I've taken so many samples, but still it is a huge difference, so this must be better. Now, even if this difference is little smaller, I will still be confident that yes, no, still given a huge sample size, it is doing better, right? But if your sample size is small, then confidence will go down. And so the basically delta mu, or let's say mu1 minus or mu1 minus mu2. If this increases, then your confidence will go up. What else? I don't know, maybe there will be more things, but let us. So, but I think this gives you an intuitive understanding that what we are talking about, right? You cannot simply say this method is better than that method, and how did you find that out? I just did one test here, one test there, and just it gave better results. That is not sufficient. You have to show statistically is it significant. So this topic is called statistical significance testing or statistical hypothesis testing. I have a hypothesis that my method is better than Nishant's method, but I may be biased, or not biased. Okay, I may pick some test samples which make Nishant a bit unfortunate that they work well for my algorithm. But to be statistically significant, to be statistically confident about my hypothesis that I am better, I have to take care of many things. Some of these things I mentioned here. Okay, take large number of samples. Even then, if my method is doing better than Nishant's method, then I'll say yes, I'm better. And also, if the difference is very large, if Nishant's model is doing very bad, then I will say, yeah, I think even if with small number of samples, I'm kind of convinced. Okay.
So what if there are two main clusters of two sets, and there's a small amount of samples far from these two clusters? So, let's say your classifier goes to takes the mean of that small sample and the mean of this whole sample, then isn't it bad? Because you wanted to classify this main two clusters, right? But you are getting the classification of this two and the small amount of samples. Like they may have some error in them. So mu1 minus mu2, I don't think it's a good way of saying that it will increase your confidence, because it might be high, but it also it can also say that the classifier is actually bad. Your clustering is very bad because you are selecting mean difference is very large compared to if you've taken these two clusters, the mean distance would be obviously less than.
Okay, so that is why we are doing randomization even while creating these sets. We are doing randomization even while creating these sets, so that our discrepancy is like this.
Shouldn't it be mu1 minus mu2 goes down? Means if the distance goes further down, then also if you are able to classify or cluster.
No, this is not mu1, mu2. See, this is after we are not clustering our data. mu1, mu2 is not the data mean. This is the mean of accuracies. Let me write down. This is mu accuracy. Means of accuracies. So if the mean accuracy of blue method is very large as compared to mean accuracy of the green method, then I'm more confident. It's not data, it's accuracy. Clear? Okay. So let us discuss a little bit about statistical hypothesis testing. We have something called a null hypothesis. So we consider two kinds of, don't look at the slides, you will be confused because so much stuff is written. So I have, let's say I want to prove something, something non-trivial. For example, Nishant's method is better than my method. Happy? So I want to prove that Nishant's method is better than my method. So this is something non-trivial. So I will make that as my, not the null hypothesis, but alternative hypothesis. What is my null hypothesis? Null hypothesis means it is both are same. Null hypothesis means both our methods are exactly same. You take the trivial case, the most trivial case, okay, that null means you are nullifying all new results, that this test is giving you some non-trivial or non-intuitive results. So null hypothesis means both our methods are exactly same. Nishant's method is not better than mine. And alternative hypothesis is that, no, our algorithms are different in the sense that Nishant's method is better than mine. This is my alternative hypothesis. So generally you take two hypotheses. Null hypothesis means the kind of baseline or the one which denies anything new. And H1 or alternative hypothesis is that which says no, a non-trivial case. No, either this is better than this or that is more significant than this, something like that, something non-trivial. Okay, so first of all, you define your hypothesis. This is my null, this is my alternative. Then you collect data, collect samples on which you want to test your hypothesis. Next step is you calculate a quantitative measure, a scalar measure to say, to quantify your confidence level, let us say. Now, if this p-value is, you use p-value to decide if H0 can be rejected. What does that mean? H0 can be rejected. If H0 is rejected, what does that mean? Yes, this means H1 is true, which means that yes, Nishant's method is better. Means the results are non-trivial or non-intuitive or something exciting. Okay, so these are the steps. First, you formulate your hypothesis, collect samples, collect the 5 samples or whatever number of samples you want. Then you compute a scalar measure called a p-value to quantify your confidence, and then use this p-value, basically compare it with a standard or threshold to say if the p-value is more than the threshold, then you say I make this decision. If it is less than a threshold, you say I make this decision. Generally what you say, if p-value is less than a threshold, you say H0 can be rejected. If p-value is more than the threshold, you say no, H0 cannot be rejected. Okay, this is just a convention, but it's okay. The concept is this, that now the main, the main thing, many main things are here, okay. First you define your hypothesis, then how are you sampling your data? The mathematical part is how you calculate your p-values. There are many ways discussed in the literature proposed by different researchers. How do you calculate your p-value which can statistically quantify your confidence? And then generally the threshold which is used is 0.05. If your p-value is less than 0.05, then you become happy. Yes, my H1 is true. And if your p-value is more than 0.05, then you say, no, H0 is true, which means my null hypothesis is fine. So nothing exciting about these results.
Is the p-value scaled to 1?
P-value scaled to 1? Yes, p-value can go up to 1. Oh, I have not defined it yet. I have just told that this is a qualitative measure of your confidence. And as we have discussed, it must depend on the sample size. It must depend on the difference of means. It must depend on the intra-class variance and all those stuff which we just discussed, right? So, but how to compute it? There are so many ways possible. We will be discussing one way which is used in this paper. What does this paper use? Can you read the this caption to the figure. Sign test. They use a sign test, which is very simple to perform, and it's good to see. So the significance level of 95%, which means 0.05, in other words, the significance level, right? So let us see what is sign test. Okay, so what is the sign test? Okay, my null hypothesis is that, okay, let me first go through this. Okay, so there are different methods, like there is a baseline here and there is KH method here, right? Baseline is, it looks like this. So this is the mean, the black dot is the mean, and this is the variance, or let's say the sigma, standard deviation. These bars, they represent plus minus sigma, standard deviation. And for KH, the mean is almost same, maybe a little bit different, but the intra-class variance, the sigma is smaller than the sigma of baseline, right? Now, can you say KH is better or not? Oh, even better is if I compare the baseline with PE. The PE, the mean is better and the variance is almost similar. What would you say? Which one is better? How many of you say, I am very confident that PE is better? Nobody? Okay. Okay, let's compare baseline with this RNH method. Baseline, this is the baseline. Compare it with the RNH, this method. Which one is better? How many of you say, I can confidently, very confidently say that RNH is better? Okay, 1, 2, 3, 4. Okay, you can raise your hands. See, I'm very confident. See, the mean is very far. Even the variances are very, means the distribution is like this. Means this is somewhere here, this is somewhere here. It's a very clear distinction that, at least what I can tell from this figure, that the RNH method is way better than the baseline, right? Okay, now how do you quantify your confidence level? So that's what we are going to see now in this sign test. Null hypothesis is that both algorithms are same, means RNH and baseline both are same. Alternative hypothesis is that no, they are different. So I have just taken some hand-cooked up values here. These values are like this. So with the algorithm 1, the accuracy levels are 80, 82, this, and for the same data set 1, for algorithm 2, the accuracy level is this much. So how do I find the statistical significance or the p-value? So what I will do is, in the sign test, I will compute the difference, algorithm 1 minus algorithm 2. I mean, accuracy of algorithm 1 minus accuracy of algorithm 2. Here it is plus 2, right? Here it is plus 1, plus 3, minus 3, right? What?
The first example,
80 minus 9.
Oh, sorry, it was 81 actually. Okay, fine. So the differences are there. So this method does not look at the magnitude of difference. It just looks at the sign of the difference. So it just sees the sign of the difference and that's it. If the null hypothesis is true, which means both the methods are similar or no better than each other, then there should be same number of positive and negative, right? Very intuitive. Same number of positive and negative should be there, right? And if one method is better than the other, then the number of positives should be very large or the number of negatives should be very large, depending on which method is better, right? This is the sign test. Now, how do you quantify it? To quantify, we assume that each of these signs, plus or minus, is coming from a distribution. Since these are binary variables, plus or minus, you can use which distribution? Binomial distribution. The output of binomial distribution is binary, 0 or 1 or plus 1 or minus 1. Right? And what is the binomial distribution? Anybody remembers? What is binomial distribution? Huh? Okay, binomial distribution is something like this. Probability of x is equal to, probability of, actually it is not x, it is the number of times you get plus sign, let us say. Okay, probability of getting a plus sign is 0.5. I mean, you call it p. Okay, let us say in general you call it any p. And probability of getting minus sign will be 1 minus p, because it is only two outcomes are possible. If one is not there, then the other one will be there. Now, what is the probability of getting 2 times 1, 2 times plus? Basically, I perform this test, let's say 5 times. What is the probability of getting 5, means 5 times plus? Means n plus is equal to 5. Or let us say n plus equal to n. What is the probability of getting n plus signs? Very good. So let us say here in this case 5cn, then p to the power n 5 minus n. Okay. And n can vary between 0, 1 to 5. Okay. That is it. So this is the distribution which we are assuming. Now if you plot this distribution, it will look something like this. This is probability of n positive is equal to n, let us say. This is your n. The total capital N is somewhere here. I don't know what is the capital N here. I just copied this image from internet. I didn't plot it myself. This is the idea. So what you can see from here is that this distribution is symmetric. Symmetric about n by 2. Symmetric about n by 2. Okay. Now I want to use this distribution to formulate a measure of confidence. Let us assume, okay, I tell you, let us say this capital N is 20. Just assume this to be 20. If I tell you I get 10 times positive, then what can you say about your confidence level? Means the p-value. P-value will be large or small? Okay, it is large, but how will you quantify it? Okay, let me give you some hint. Let us say if my n is this, right? If my n is very small, let us say 0, 1, 2, something of that sort, are you more confident or less confident about the alternative hypothesis?
N is total.
Small n, yeah, capital N is total. More confident about the alternative hypothesis. So if my small n is very small, then my probability of null hypothesis goes down, right? If my n is very small. If my n is very large, let us say somewhere here, still the same, right? Which means if my n is either close to 0 or it is close to capital N, then my p of h naught will be very small. But if my n is somewhere in the middle here, if my n is somewhere around n by 2, then the probability of null hypothesis will be very large. Okay. Now how I quantify is, So I measure the integral, the area under this curve or this histogram, the area under this curve up till this point, including this point. Basically, this area plus this area. And I call this as P. Means, oh no, this P is different from that P. I call this as, let me call this as P dash so that we don't get confused. So my P value, okay, let me call it as P value. My P value is this area plus this area. So basically, this area plus this area. Huh? Why? Because I want to formulate a p-value such that if my n is close to 0 or capital N, then my p of h0 should be very small. Let us call this as a p-value. My p-value quantifies p of h0. It does not quantify, but it is like my confidence. If my p-value is less than 0.05, then I will reject my null hypothesis. If my p-value is more than 0.05, I will accept the null hypothesis. So this is how I quantify my p-value. I say, if I get n, this one, if this is my n, you find the area under the curve below this n and the area under the curve above n minus n. And if that area, call that area as your p-value. If that p-value is less than 0.05, you reject the null hypothesis. If it is more than 0.05, accept the null hypothesis. Right? If my p-value, if p-value is less than 0.05, then reject null hypothesis. This is my rule which I have created. This is 95% significance level or 5% significance level, whatever you want to call it. Is this clear? So basically I am calculating the area under the curve. If that area is, I call that area as the p-value.
Is it because of that there's a chance that the value, probability value of n plus equals to n, even if the p of h0 is at its maximum, it might be less than 0.05. And to avoid that, we took integral. Because then if it's in middle, then
Yes.
value will be 1.
Yes.
Half plus half.
Yes, you are right. You are right. So we take the integral from 0 to n so that
It does not go below.
yes. Okay. So my h0 is true if basically this is my p-value if it is more than 0.05, right? This is my p-value. But if it is less than 0.05, then I am happy that my null hypothesis is not correct. Then, okay, we have already discussed these equations. I think that's it. So let's go back to the paper. In this paper, if you find the p-value or the significance level of difference between the baseline and PE, it comes out to be very small. The p-value is larger than 0.05. So null hypothesis is accepted. So these two methods are not statistically different. Means it looks like that PE is better than baseline, but statistically it is not significant. You are not confident. How can you become confident about it? Yes, take more samples. What will happen if you take more samples? Basically, this distribution will become more fine-grained. Instead of becoming like a histogram, it will be more smoother, right? So let us say your p-value is somewhere here. Means your n is somewhere here. Now the area will be smaller because your, let us say, let me take an extreme example. Something of this sort. if I get this value now, certainly my p-value will be larger than 0.05, right? I have taken so big steps that the quantization will bring so much into the p-value.
Doesn't it depend on how you quantify it? In integral, we take one quantization which has area greater than actual area, and one quantization which has area less than the actual area. So
No, this is not this is histogram, no? Because if you have less number of, in this case, the capital N is 5. In this case, capital N is, let's say, 500. Right? This is fine-tuning because of sampling. We're sampling very close. Huh? Number of bins. Yeah, number of bins. Okay. So it is possible that by increasing the data size, you may get the results may become statistically significant because the p-value is inversely proportional to capital N. Can you see it from here? P-value is inversely proportional to capital N. I can't see it. It's not obvious from here, but that's what you get when you kind of. I think I've not done this analysis yet. Okay, another point which I want to discuss quickly is, okay, majority of the submitted systems use discriminative training. What is discriminative training? Like neural networks is discriminative training. What is not a discriminative training? Generative model like GMMs, they are not discriminative training because to train GMM, you do not look at samples from other classes also. You just look at the samples from the same class. You don't discriminate. You do just generate the data. Okay. Something which I wanted to discuss important is, yes, a simple majority vote classifier. We have discussed this method earlier in ensemble methods or bagging. So if you have many classifiers, if you combine all of them to construct a single classifier, many times, that single classifier will do better than the individual classifiers. What was the reason which we gave for this? If I have individual, let's say, 10 classifiers, and they give me some levels of accuracies, now I construct a new classifier by combining the results of all these classifiers, by fusing the results. I may use a majority rule, right? If, let us say, out of these 10 classifiers, 6 or more say this is the class, let's say it's a binary classification, okay, let us say. Or if it is not binary, then it is n-class classification problem. If majority of my classifiers say it is this class, then I will go with that class. So in majority of the cases, this kind of a majority vote-based classifier will be better than individual classifiers. Can anybody tell why? Why is that so? We have discussed this.
Due to the
Randomness in what?
Will approach the same border from different sides.
Yes.
So there's
Yes.
a high probability that.
So in other words, in more precise words, that it is very unlikely that every classifier will do the same mistake or will misclassify the same sample, right? For example, if you have an exam and all of you team up, certainly you will get much better marks, the combined marks. Because let us say somebody does not know answer 1, somebody does not know answer 2, but if they team up, then they know more, right? That's why people copy. This is one of the prominent reasons. They want to do some bagging. So that is what they have also observed. If you see this red one, this result is from the bagging-based classifier, or what they call it as, the majority vote-based classifier. And it is doing the best. Okay, just one point we missed. What is chance level? What is chance level? Yeah, so basically any test sample comes, you randomly give it some value, Let's say I've got 10 classes. I randomly assign one class. What will be the accuracy of this classifier? Yeah, almost 1/10 of the time it may predict correct. So the accuracy will be about 10% if there are 10 classes. If there are 5 classes, then accuracy will be, the chance level will be 20%, 1 upon 5 basically. So 1 upon n. Okay, that is the chance level. Okay, anybody has any questions here? I can discuss more things, like you can see confusion matrix, or no, this is just, here we have different methods, here we have different classes. Okay. Anybody has any questions or regarding what we discussed today? Maybe this hypothesis testing or something. Okay, there are different ways to compute p-values. Sign test is certainly not the best because they ignore the magnitude of difference, they just take the sign. There are other methods like student's t-test, which is very popular, people do it. Student's t-test, so the basic idea is, instead of considering this as a binomial distribution, they consider it as a student t-distribution or a kind of a normal distribution. And then they look at the tail. So in this case, they are looking at both the tails because both the tails are important, right? Either one is better or the other is better. But you can also, there can be a situation where I want to just evaluate, is this better? Then your null hypothesis is that, okay, Nishant's method is not better than me. That is a null hypothesis. And the H1 is that Nishant's method is better than me. Then I won't look at both the tails. I will just look at one of the tails because that is what I'm interested in. Right? Okay. So please ask questions. We have 2 minutes for questions.
If we keep thresholds same in the both cases, we are just considering one-sided integral and both-sided integral, would it be unfair to both the systems? Because one is considering from the both sides, so obviously it will get a lesser amount of x-axis, and that will get more amount of variation. So you will have the same threshold.
Yeah, it's true. So that is these are the conventions or our predefined notions which we, before even doing this data collection, we define these notions that yes, I'm going to do a double or two-tailed test or a one-sided single-tailed test, two-sided or single-sided basically. So, and what is my significance level, 95% or different value, and what is my null hypothesis, what is my H1, all these are decided before, and then you go for the test. All right.